Now we are going to discuss about the shapes of atomic orbitals. Before we discuss the shape of atomic orbitals, let us try to fill this table on the basis of quantum numbers that we have discussed. First column we have n value, second column the name of the main shell, third column L value, 4 number and name of subshell, 5 number and name of orbital, and the last column we have number of electrons in main or subshell. So first n is equal to 1, n is equal to 1, main shell is k, and L is equal to 0 because we know that L value ranges from 0 to n minus 1. Now number and name of subshell, number of subshell is the nth shell is equal to n. So we have one subshell and the name of the subshell is given by L value, L is equal to 0 is S subshell. Now number and name of orbital, if you know the value of n, number of orbitals is equal to n square. So here we have 1 square, so we have 1 orbital and name of orbital is same as name of subshell, so it is S orbital. Number of electrons in main or subshell is given by 2n square. So 2 into 1 square is equal to 2. So you can see in the K shell we have one subshell, that is S subshell, and we have one orbital in S subshell, let's call the S orbital, and you know any orbital can accommodate a maximum of only 2 electrons. So number of electrons in S orbital is equal to 2. Now n is equal to 2, we have main shell L. Now the values of L is 0, 1. Now we have 2 subshell, or if you know the n value you can write the number of subshell. Number of subshell is equal to value of n. So 2 subshells, and the name of 2 subshells are S and P because L is equal to 0 is S and 1 is equal to P. Number and name of orbital, number of orbitals is given by n square. So here we have 2 squares, so 4 orbitals. Now the 4 orbitals are, we have S orbital and P orbital, that is we know there is only one S orbital and we have 3 P orbitals. So total number of orbitals will be equal to 4 and number of electrons will be equal to 2n square, that is equal to 2 into 2 square, which is equal to 8. Now next, and you know each orbital can accommodate 2 electrons. So we have total 4 orbitals, means 4 into 2, 8 electrons. Now n is equal to 3, m main shell, the values of L are 0, 1, 2, and we have here the number of subshell is equal to value of n. So 3 subshells and the subshells are S, P, D. Now the number of orbitals is n square, so we have 9, n square, 3 square is equal to 9 orbitals. And how we get this 9 orbitals? 1 s orbital, 3 p orbital and 5 d orbital. So 5 plus 3 plus 1, 9 orbitals, and 9 into 2, 18 electrons can be placed, or you can use the formula 2n square. Now next we have n is equal to 4, n main shell. The L values are 0, 1, 2, 3 and the number of this column is number and name of subshell. So number and name of subshell is equal to 4 subshells S, P, D, F. Now the number and name of orbitals is, since we have 4 subshells, n is equal to 4, so n square means 16 orbitals. How we get 16 orbitals? 1 s orbital, 3 p orbitals, 5 d orbitals and 7 f orbitals. So 1 plus 3 plus 5 plus 7, we get 16. Now we have the number of electrons, 2n square, 2 into 4 square, which is equal to 32 electrons. Okay, so this is the table. Now next let's see one more quantum number, that is spin quantum number. 4, spin quantum number. denoted by S, small s. We know that an electron in an atom can have two spins. One, it revolves around the nucleus. Second, it rotates or spins on its own axis. So we have two values for spin, and the two values or two rotations possible is one in clockwise and one in anti-clockwise direction. So the values of spin quantum number or values of S is plus half and minus half. So these are the two values of spin quantum numbers, and we can say that there are two spin states for an electron. They are spin up, and spin up is denoted with up arrow, and spin down with a down arrow. So if there are two electrons in an orbital, one electron will have spin up and the other electron will have spin down. That is, one electron will move in clockwise direction and the other electron moves in anti-clockwise direction. So these are the two spin values, plus half and minus half. So this is spin quantum number. Okay. Now next, let's see subshell notation. Denoted as NL. N is the principal quantum number and L is the azimuthal quantum number. Now, if you are given the orbital as 1s orbital, 1s. 1s means we have, if you see this, you can write n value, L value and m value. Here n is equal to 1 because the notation is NL. So n is equal to 1 and L is equal to 0 because we know that L is equal to 0 is S subshell. If you know L value, you can write the m value. M can have 12 plus 1 values ranging from minus L to 0 to plus L. So if L is equal to 0, m is equal to 0. Okay, now the spin, if there is only one electron in 1s orbital, then the spin can be plus half or minus half. And if there are two electrons, one electron will have plus half spin and the other minus half spin. Now next we have another example, 2p. Here n is equal to 2, L is equal to 1, m is equal to minus 1, 0 plus 1. Now 3d, n is equal to 3, L is equal to 2, m is equal to minus 2, minus 1, 0, 1, 2. Because we know m can have values from minus L through 0 to plus L. Now we have 4f, n is equal to 4, L is equal to 3, m is equal to minus 3, minus 2, minus 1, 0, 1, 2, 3. 7 values. So again you can see this s orbital will begin with n is equal to 1. So here we have 1s orbital, 2s, 3s, 4s, etc. Now p orbital begins with n is equal to 2. So we have no 1p orbital. P orbital we have from 2p, 3p, 4p, etc. D orbital begins with n is equal to 3. So we have d orbitals from 3d, 4d, 5d, etc. There is no 1d, 2d orbital. Now f orbital begins with n is equal to 4. So we have 4f, 5f, 6f orbitals, but no 1f, 2f, 3f orbitals. Now if you look at this m value, we know that m value gives the number of orientations. S orbital we have only one value, so one orientation. Here p orbital has 3 orientations because we have 3 m values. So, and also we know there are 3 p orbitals. Now this d orbital has 5 orientations because we get 5 values for m and there are 5 d orbitals, and f has 7 orientations because we get 7 values for m and we have 7 f orbitals. Okay, so this is subshell notation. Now let's see about the shapes of atomic orbitals. Shapes. of atomic orbitals. Now, we are going to study the shape of s, p and d orbital, and I told you in chemistry in class 11 and 12, you need to study only about the 4 subshells s, p, d and f. So, we have the 4 orbitals s, p, d and f orbital, but the shapes you are going to study only for s, p and d. So, let us see the shape of s orbital. Now, s orbital is spherical in shape. Now, if you are asked to draw the shape of 1s orbital, we have at the center nucleus, and around the nucleus we have close to the nucleus. We have the probability of finding electron, and this is the shape of 1s orbital. Now, I am going to draw the shape of 2s orbital, and you can see the shape is spherical in shape. 2s orbital means first in the middle we have the nucleus, close to the nucleus we have 1s orbital. Now, here we have maximum probability of finding the electron. Now, we have vacant space where the probability of finding electron is 0. Again, after that space we have more probability of finding the electron, and so this is our 2s orbital. So, this is the shape of 2s orbital. Okay, so we have first nucleus, close to the nucleus 1s orbital, then we have a space where the probability of finding electron is 0, and we call this space as node. Nodes. Nodes are region of space around the nucleus where the probability of finding electron is 0, or the probability density function reduces to 0. They are called nodes. And next, if you are asked to draw the shape of 3s orbital, then we have nucleus at the center, close to the nucleus there is maximum probability of finding electron, which is our 1s orbital. Again we have nodes, after that again we have more probability of finding the electron, that is our 2s orbital. Again we have another node, after that again we have a region where the probability of finding electron is maximum, and this portion is 3s. So, this is the diagram of 3s orbital. So, you can see the number of nodes in 1s orbital is 0. 2s orbital we have 1 node. 3s orbital we have, this is 1 and this is the second one. There are 2 nodes in 3s orbital. So, you can see as n value increases, the number of nodes increases. Now, there is an expression to find the number of nodes in any orbital, and that expression is number of nodes in any orbital is equal to n minus L minus 1. This is the expression. And for s orbital, we have L is equal to 0. Therefore, number of nodes in s orbital is equal to n minus 1. So, you know that in 1s orbital, number of nodes is equal to n minus 1, it is equal to 1 minus 1, 0. Now, in 2s orbital, the number of nodes is equal to 2 minus 1, 1 node. In 3s orbital, number of nodes will be equal to 3 minus 1, 2 nodes. So, as n value increases, the number of nodes increases. Okay, thus we can say any s orbital, let it be 1s, 2s, 3s, 4s, 5s, they all have the same shape, that is spherical in shape. But they differ in the number of nodes, size and energy. Okay, and as n value increases, the number of nodes, size and energy of the orbital also increases. Now you can say as the increasing order of energies of s orbitals, increasing order of energies of s orbital is 1s less than 2s less than 3s less than 4s less than 5s, etc. So this is the order of increasing energies of s orbital. Now next let us discuss the shape of p orbitals. Shape of p orbital, and the name of the shape is dumbbell shape. Now we know that p orbital has a dumbbell shape, and you know there are 3 p orbitals because there are 3 values for m, which means there are 3 orientations for p orbital, and the name of 3 p orbitals are px, py and pz. So these are the 3 p orbitals in p subshell, px, py, pz. When I say px, the orientation is along x-axis, py along y-axis and pz along z-axis. Now I will draw the shape of 2px, 2py and 2pz orbital. So first I am going to draw 2px. This is x-axis and this is y-axis and this be z-axis. So px means we have the orientation along x-axis. So this is the shape of 2px. 2 means, you know, the subshell notation is nl. So n is equal to 2 and it is p orbital, 2px. Now here you can see in 2px this is the dumbbell shape, and here we have 2 lobes, L-O-B-E-S, 2 lobes. This is one lobe and this is the second lobe. 2 lobes on either side of the plane that passes through the nucleus, and the probability of finding electron is 0 where the 2 lobes meet each other, and the probability of finding electron is maximum and equal in 2 lobes. Okay, so this is the shape of 2px. Now 2py, x, y, z. 2py will be along y-axis. So this is the shape of 2py. Now next let us draw the shape of 2pz. 2pz will be x, y, z. 2pz will be along z-axis. This is the shape of 2pz orbital. Now you can see the 3. So this is the shape of 2px, 2py, 2pz orbital, and all the 3 have same size, shape and energy. 2px, 2py, 2pz have same size, shape and energy. But when the n value changes, that is if it is 3px, 3py, 3pz, 3px, 3py, 3pz have same size, shape and energy, but the size, shape and energy of 2px and 3p is different. Okay, so you can see that they have same, all 3 2p orbitals, that is 2px, 2py, 2pz have same shape, size and energy. Now the expression to find the number of nodes, you know, the number of nodes is n minus l minus 1. Now for p orbital we have n is equal to 1. Therefore number of nodes in p orbital will be equal to n minus 1 minus 1, which is equal to n minus 2. So if you are asked to calculate the number of nodes in 2p orbital, we have number of nodes is equal to 2 minus 2, 0. Now 3p orbital has number of nodes is equal to 1. 4p orbital has number of nodes is equal to 2, and so on. Now I told you this 2px, 2py, 2pz. These three orbitals which belong to the same subshell, that is n is equal to 2, has same energy. Okay, and we call this as degenerate energy levels. So what do you mean by degenerate in orbitals, or you can say degenerate orbitals? Degenerate orbitals means orbitals with same energy. So if you take same n value p orbital, all three will have same energy. So we can call them degenerate orbitals. But I told 2p and 3p has different energy, 3p and 4p has different energy, but 4px, 4py, 4pz has same energy, same shape and same size. So this is about the shape of p orbitals. Now let's see the shape of d orbitals. Shape of d orbitals. Now we know that there are 5 d orbitals. Okay, because for d orbital SPD, L is equal to 0, 1, 2. L is equal to 2, and we have m value as -2, -1, 0, 1, 2, which means how many orientations are possible? 5 orientations are possible, and we have 5 d orbitals. Now the shape of d orbital is also dumbbell shape. Now the d orbitals, I'll write the name of 5 d orbitals. They are dxy, dxz, dyz, dx square minus y square, and dz square. Now these 5 d orbitals have same energy. Suppose it is 2dxy, n is equal to 2, 2dxz, 2dyz, they all have same energy. So we can call these 5 d orbitals as degenerate orbitals. And the number of nodes in d orbital is n minus l minus 1, and l is equal to, what is the value of l for d orbital? 0, 1, 2. Now number of nodes. Is given by n minus l minus 1, and l is equal to 2 for d orbitals. So for number of nodes is equal to n minus 2 minus 1, which is equal to n minus 3. So we know d orbital begins with n is equal to 3. So we have number of nodes for 3d orbital will be equal to 3 minus 3, which is equal to 0. Now I am going to draw the shape of all 5 d orbitals. Now dxy I am going to draw first. This is dxy. Now next we have dyz. So you take this as y and this as z axis. I told the shape is dumbbell shape. This is the shape of dyz orbital. Now next is dxz. This is x axis, and take this as z axis. This is dxz orbital. Next we have dx square minus y square. That is along the axis. This is the shape of dx square minus y square. Now Last we have dz square. This is z, so the shape is like this, dz square, and it is a donut shape. This is the shape of dz square. So the 5d orbitals shape is like this, and the 5d orbitals are degenerate. Okay, so with this the shapes of atomic orbitals is over. Thank you.